All right, we're going to get started with session 4, right?
Yeah.
Okay, we're on session 4. So there's nothing that kind of wakes people up in the afternoon like a nice dive into statistical details of models and machine learning. So that's why we planned it for this very time, to really wake people up. So don't all jump at once. No, but in all seriousness, so David Dunson, Evan Poworoznek.
Good. No, that was good. No, he got it.
I got within like nearest neighbors of it, right? Yeah. Kelly Moran are going to be talking a little bit about some. So let me just back up a little bit. We've heard a lot about machine learning, these kinds of modeling for predicting various outcomes, and I think in this session, what we want to do is look under the hood, look, and see how these things work and how you might actually be able to implement them in real life. And so they are going to talk about that and show some examples, some code examples, kind of running in R. So take it away.
Thanks a lot for the invitation. And so if you haven't yet, in your program book, there's some sort of instructions for downloading. Also, some people have done it. Maybe if they're sitting at tables, you can kind of look around at their computer. So I'm just going to give a brief kind of context for what the hell is going on. And then Evan will talk a little bit more about some of the details of the kind of modeling, the moving pieces. And then Kelly will lead the kind of the active demo part of things. Okay. And so this is some of the team. There's a couple of other members in the back. Sorry, it's jumping around. For this PRIME project we have from NIHS, which has kind of motivated all of this. And so we're really interested in, here's kind of an overview of the grant, but we're interested in assessing the health effects of mixtures and kind of coming up with new machine learning, AI, statistical tools for doing that, using kind of a combination of information like mechanistic information, chemical structure data, and toxicological responses from like ToxCast, which is, jumps a lot, can't point, which is what we'll be talking about in the demo. And also we're doing a lot on kind of trying to come up with just completely new methods using Bayesian ideas and dimensionality reduction and factor modeling to try to integrate data across these different sources and making sense of health effects of chemical mixtures, okay? So that's the basic game. I'll skip forward. And so it's really a big thanks to NIHS and the PRIME project, which is what funds all of this. And I'll start out with a motivation, okay? And so people have seen this a lot today already, and so I'll basically just skip over it. But the bottom line picture is that there's like 1 billion different chemicals that we're all exposed to all the time, and we don't know what any but a small fraction of them do to our health. And we just kind of assume that they don't do anything, hopefully, and just kind of go about our lives hoping for the best. But we'd like to have some sort of automated methods for making sense of the chemical effects. And what we're particularly interested in is doing something like taking chemical structure features from different chemicals. And we do it in one way. There was a couple of really awesome talks that I was really stoked about this morning where they were talking about other ways to do it, which are probably better than the ways we're doing it because we don't know anything about those things. But we'd like to take the chemical structure features and actually be able to link that to the toxicological responses and then even the epidemiology data, and then do that in an automatic way. And so then you could take a new chemical and then I could even predict the dose response with uncertainty for the new chemical, okay? And so that's the sort of exercise we're gonna kind of be talking about today in the demo. Yeah, so we're gonna be using data from the ToxCast program. And so many of you are familiar with that already, but we'd like to replace these kind of really slow animal studies with this kind of fast, high throughput screening. And so if we have data from the ToxCast program, we have it over 9,000 chemicals, 1,000 different assay endpoints. That seems to be a perfect opportunity for machine learning. And then maybe for each of those chemicals, we can also extract a bunch of different chemical structure features, and then we can kind of do some type of machine learning method to borrow information and then be able to, in a de novo way, predict outcomes for new chemicals that haven't been studied. Okay, so some information that's relevant to what we're talking about. Some assays are more relevant to toxicity than others. Today we're just going to be in the demo focus on one, which is the Adogene PXR assay, or we'll also use simulated data, but that's what we used in kind of developing our method as a test bed. For chemical structure, we quantified it using what's called MOLD2. okay, and we can get a dose response as well. So just skipping forward, so we're going to have chemicals that are different, have different structures. This mold2 thing will spit out a feature vector, which is almost 800 dimensional on each of these chemicals. Hopefully, then we can do some sort of machine learning to tell that certain of them are similar in structure, and then maybe similarity in structure would hopefully then maybe apply to similarity in response. Okay. And so yeah, mold2 generates 777 chemical descriptors. I don't know exactly how it does it, but we just take it as a black box at this point. If you have ideas about better chemical structure features, email me. I'm super interested in that. And we have a whole bunch of different completely new types of machine learning or Bayesian, or not even Bayesian, but just dimensionality reduction methods that we're developing that provide maybe much better versions of PCA that can capture nonlinear structure and high dimensional data. So we're kind of really, I think, at the state of the art in that, and we'd like to test these things out on lots of different data sets. And so if you have these kind of high dimensional environmental health data sets, chemical structure features, other things that you're measuring, different things you're measuring that you'd like to link, we're super interested in that. And we have a lot of tools we'd like to try out. Okay, so we have like this chemical structure feature, and then we also have these dose response curves, okay? And so this is bisphenol A, and we have these kind of dose response curves with uncertainty for different chemicals, different assays, and we'd like to kind of tie this all together. Okay, and some chemicals might be near in structure and far in activity, and so even though chemicals are really similar, that doesn't mean that they have similar dose response curves. And so we'd like to have something that can kind of capture that uncertainty, maybe using a type of Bayesian method that actually Kelly developed. Okay, so our model goals are to learn a low-dimensional subspace underlying both structure, and activity. We'd like to develop sort of a distance metric for chemicals relying only on structural features relevant to toxicity, which was the same goal as a talk this morning. We'd like to be able to handle very disparate types of data, irregularly spaced dose response curves, having different types of measurements. Yeah, and if you have chemical predictions, even for chemicals having no observed dose response information. And so I'm going to switch to Evan, who's going to hopefully quickly tell us a little bit about the nuts and bolts of the models we're going to be using, and then we'll go to this kind of demo part. Okay.
There's a little preview that will. Sorry. Oh wow, that's handy. This is a preview. This is what we'll be talking about in a little bit. Just get ready for it. We'll come back once we've introduced some building blocks that I think will help you sort of digest what all this structure means. So I want to talk about two things to like sort of lead into Kelly's presentation that's going to use these two features for some good work. There's factor modeling, which some of you may be familiar with already, and Gaussian processes, which also are a pretty standard concept in statistics. And yeah, so I'll start with factor modeling. First, we want to sort of talk about like what a model is and what we do when we learn. We like to consider every single aspect that goes into this process. So we start with the data, which comes to us in the form of a study usually, and we have structure in there. We have maybe multiple responses, maybe some of them are longitudinal, maybe our features are not all things that we're interested in. We have covariate information that may represent a significant effect, say on like birth weight or something, that is important to consider if we want to make any sort of statements about association of chemicals and the outcomes, but is not something we're directly interested in. So we really want to like get a handle on the structure in our data. We want to learn what that is. And at the same time, we want to like have a model that we can perform inference on, that we like know what the parameters mean, and we can do some sort of hypothesis testing or interval estimation for what the underlying features are that are driving these relationships. And at the end of the day, we also want some predictions coming out of this that can tell us, are these chemicals dangerous? Are they safe? And what are the uncertainties around those predictions? So we consider each of these sort of points in the model really specifically, and I'll circle back to this sort of understanding as we go through this sort of building block presentation. First, we want to talk about the structure in the data. And this is a really common issue with our chemical data, but also in general epidemiology studies where there are a lot of highly related features. And in this graph, which is from the Mount Sinai birth cohort study, which is a really high quality data set studying mothers during pregnancy and a bunch of related outcomes for the children, we see that there's a lot of linear association between the chemicals measured in the urine samples taken in the second trimester. And this structure is both harmful if we don't consider it and useful if we do. So we really want to both consider this carefully, and maybe at the beginning we don't know this structure. We don't have necessarily empirical evidence for all of these associations that we can analytically type into our model from the get-go. We want to learn it as we do the study. As we do the analysis, we want to learn the structure with the parameters. And I think there are a lot of sort of definitions of machine learning, but one of the ones I like to come back to is we're not just writing down a model and learning the parameters. We sort of learn the data generating function as we learn the parameters. And that's sort of like what maybe comes about with this sort of automated artificial intelligence paradigm. So to directly relate it to the demo we'll be doing in a couple minutes, we start with the ToxCast data, which has a lot of information on some chemicals, and the MOLD2 feature generator, which can give us descriptors on basically any chemical we can write down in smiles, which is useful. And if we consider the structure that comes into both of those data sets, it's not just some sort of random positive association. We have a similar case to the structure in the epidemiological data where there are groups, there's negative associations, there's real strong linear structure. Like, for example, if you're considering the predictors, the amount of oxygen in a molecule and the overall atomic mass, those are going to be highly related because molecules with more oxygen will have a higher mass in tendency. So we want to take that information into account, and we don't want to ignore it. And some of the other methods that are common in this case, where we have a lot of predictors and high relationship or a lot of relationships in the data, is lasso and stepwise selection. But these only take that additional variance element that we get when we have a lot of predictors and a lot of relationships, and they remove it. They reduce the variance, but they don't consider the structure directly, and they don't learn from that. And if we think a little harder about the problem, we definitely can learn something. So we're interested in modeling this linear association and this linear relationships within the data. So we have this handy linear algebra factorization that we use, where we start with all of the relationships in the data. That's this big omega matrix over here, which is about p squared parameters, which is a lot usually if you're measuring 777 chemical descriptors or however many features you have in your epidemiological survey. And we reduce it into, using this factorization, into a factor loadings matrix lambda, which is k, which is the number of factors by p, and this noise term sigma. And k times p to p times p might seem a little arbitrary, but k in this case can be much, much smaller. And if we estimate k times p parameters, where k is much smaller than p, instead of p times p, we can much more efficiently use the information that we have because we're learning fewer parameters because we've taken advantage of the structure that we found in the data. So our goal is to learn a lower dimensional representation in order to have a better understanding of the structure, but also more efficiently use the information that we have. And then additionally, on top of all of this, we can do inference on the structure that we find in the data and really get some new information out of it that isn't available directly if we just do lasso or something like that. So there's a math form of the model that we're sort of circling around here, and this is a generic factor model. If math doesn't suit you, that's fine. The most important thing to note is that this lambda matrix, it's in two equations at the very top and very bottom. That is the same lambda as was in this sort of fun graphic. So the notation's the same. This lambda is a common theme. It's a factor loadings matrix. If a lot of you are probably familiar with PCA, it's very similar to the matrix that you get in principal components analysis if you truncate at a certain point along the, like, say, 5 principal components or some such. And we can see directly that PCA is a competitor for this method and not one that does too well. PCA has some standard issues that some of you may be familiar with, in that it's extremely sensitive to what data you collected, and it's very hard to do inference on. Just as an example, quickly, here we have the NHANES data for 2015, subset into 2 400 observation data subsets, and we run this latent factor model as being described and principal components analysis on each of these subsets. And we find that we get really different results if we just do standard principal components analysis, but the latent factor model, because we are a little more careful in how we define it and how we sample it, it leads to much better results in general. And the sort of stability that we find in the latent factor model is one of the main benefits, where a lot of machine learning methods can be very uninterpretable and somewhat difficult to work with because we have these sort of scary thoughts about what if what I am looking at is not reproducible in any way. In this model, you can really inspect every element of it and see what's going on underneath it in a way that's much more interpretable. There are also some other methods that are a little more advanced that we consider when we write a model down like this, where we're modeling the linear association in this large feature set. Obviously, the extension then is, what if there are nonlinear relationships? And well, our general answer is we're working avidly on that. But for now, linear approximations are good in general. We find them to be a good place to start, and especially if you don't know much about the size of the space that you're working in and a whole bunch of other assumptions that go into some of these more complicated methods. It can be either a good building block or just a good place to be because you're making assumptions, but they're fairly safe. And also all of these more nonlinear methods that are a lot more black boxy also come with a lot more data sensitivity, and generalizing beyond the data set that you collected is a very difficult assumption to make. So, like, in what ways do we benefit here specifically? We have a great new class of analysis in factor modeling, which is semi-parametric. And the overarching theme, and why it connects back to the machine learning definition I described earlier, is that we don't necessarily know how many factors are in our data set that we start with. Like, in the same way that when we do a principal components analysis, we don't know how many principal components it's necessarily good to choose. We have the same problem here. But thanks to some work by David earlier, we have a nice prior to use in our Bayesian analysis that allows us to learn how many factors can accurately represent this data. And so in this way, we're really learning the model as we learn the parameters, because we're learning how many factors should be in our model and how many parameters overall we should estimate. So in a way, this is sort of how complicated is the relationship that we're looking at. And we have a nice, simple, automatic way to find it. The second building block I want to touch on are Gaussian processes. In this case, we're modeling dose response, which is a function, and we're modeling it through a sort of additive mixture of functions. So in the end, we need to be modeling a function, not just simple point estimates. But we can do that in a really straightforward manner by treating that function sort of like how we would model a point estimate, where there's a value that we want to predict, so we have a point that we think is the best, but then we have a sort of uncertainty interval around it. And by using Gaussian processes, we can develop that point estimate function. Here it's in black. And then we can sample this function a lot in our Bayesian paradigm and come up with an interval of expected space that the function can live in. And through that, we can sort of generate all of the sort of interval estimates that we can for a point estimator, but now for a function. And this is really useful if we want to estimate something smooth like a response. And yes, we are Bayesian now, so we do have to think a little bit about the prior and the likelihood that we're using. In this case, we'll be using a lot of shrinkage priors. So here we have a zero-centered normal-normal model. The important part here is that we're quantifying our prior information and inputting it into our model in a way that's rigorous and robust. And the model that we write down and the data that we collect is formed in this likelihood. And our posterior, which represents our total understanding of the situation, is a mixture between what we thought before we started and the data that we collect now. And this posterior, we're more certain in than we were in the data that we collected or the understanding we had before, because it's a mixture of both of them. And in this case, the thing that we expect is sparsity. We expect that a lot of the parameters that we write down in this model are actually zero. Because if you think back to like the earlier or this is MSSM. If we think back to the study, if we're trying to measure all the like information in an efficient way that's in this data, and we start with our original data matrix full of features, we might believe that efficiently represented, this information here is some numbers and then a lot of zeros, because we have some redundancy here. Not all of the features are measuring independent things. So there are a lot of shrinkage priors to choose from. We'll talk a little bit later about some others, but for some parameters, we like to use the horseshoe prior because it has some great properties where for unimportant things that are nearly zero in the first place, it shrinks them to zero very effectively, which is the behavior that we want. And for things that actually show a true effect, it shrinks them very little, which is sort of the optimal solution. And while we're in this Bayesian paradigm, we get to sample things, which some people think is an impediment, but I think is pretty great because we get a distribution for every single one of the parameters in our model. And by sampling and taking these samples, which are the output of all the functions that we use, we can perform any sort of summary function we want. We can get an interval estimate, we can perform a hypothesis test, anything that we actually want to get from these parameters, any sort of information we want to take away, are in these distributions. And so by when we run our functions and when you run the code later today, you'll get samples out. Those samples really represent all of our understanding about this model and the parameters that we're working with. So we'll have a direct application of that later. And the main sale point of a lot of Bayesian methods and the really easy extension then is that we have immediate uncertainty quantification, because when we have a distribution for every parameter and we want an interval estimate, we can just take the middle or the highest probability, that doesn't really matter, 1 minus alpha of the distribution, where alpha is our significance level, and we get an interval estimate. And here we can even get interval estimates on parameters that are typically inestimable. So for PCA, there's no sense of uncertainty about what the loadings are supposed to be. If we correctly align all of our samples of lambda, we can actually get an interval estimate for group membership and antagonism and things that are really helpful for understanding the structure in our data, but are typically hard to estimate. But that's not immediate, and we do have to apply some post-processing for that to be possible, because say you're trying to estimate x, but you only ever see x squared. You don't know if it's positive or negative. And we see something really similar in this lambda transpose math, where we have a rotational unidentifiability. But we provide post-processing functions which majorly alleviate this issue. So now we're back to the graph. Hopefully we sort of understand what the squiggles are now, which are functional responses. And we're starting to understand the lots of lines, but Kelly will do a lot better explaining those than I can. So I'd like to introduce Kelly.
Thanks, Evan. Great overview. So I want to provide just a touch back to the intuition behind what our goal is. And the goal is that we have a matrix of chemical features, and we also have some matrix of chemical dose response information. So here, if you look at the visualization on the right side of the right figure, the red lines are our dose response curves, and each row corresponds to a different chemical. So we see in the first row, for example, that we have a fairly flat dose response relationship until we get to higher doses, and then it appears that there is some effect, toxic effect. And then the X matrix on the left side of that figure is our feature vector. So with the mold 2 example, we would have 777 columns here, providing things like the number of oxygen, the molecular weight, various chemistry terms that I don't really know very much about. And what we want to do here is we want to link our structure to our dose response. And so mathematically, if you look at the very top of the figure on the far right, we have these terms, eta, and the lines here represent probabilistic dependency. So what happens is we have these latent terms eta that we don't actually observe that impact both our structure and our dose response. And what that looks like mathematically is in the left equations here, we have yi and xi, and that represents the dose response curve for chemical I, the d length vector y here, and the 777 dimensional feature vector x for chemical I. And we see that we're assuming that all of our variation in y, our structured variation, is explained by this term lambda times eta I. And the lambda here is the loadings matrix in a factor model, just like Evan was describing earlier. And then our epsilon I here is just some random noise. So that's why we don't observe perfectly the points along this dose response curve when we see dose response measurements. And then down below, the vector x is comprised of the product of theta times eta I. And so we see that eta is shared between the x and the y. So our latent factor is shared between dose response and features, but we have a different loadings matrix for the two of them. And then the additional additive term in the xi equation here is just providing some additional structure that we're allowing to exist but not impact toxicity. And so the way to think about that is that there's likely a lot of chemical structure components that are important for toxicity, but similarly, there's likely a ton that are not important to toxicity at all. And so we want to make sure that we don't just assume that x and y are both fully explained by this shared latent factor eta. We want to allow x to also have this additional piece. And so to put this a little bit more formally, here we're getting into why Evan spent some time talking about Gaussian processes. Our y is a functional response, since y is a dose response curve. So what we want is we want the columns of our loading matrix lambda to be functional in nature. And so we model each column of lambda as coming from a Gaussian process. And so the term lambda times eta I ends up being the sum of all of these different functional curves. And so the result is also some function. And then what we do is we apply shrinkage on successive columns of this loadings matrix so that as we get further and further over in columns, we just get closer and closer to a flat curve. And so that allows us to not have to perfectly know the number of factors k, as Evan was describing. We can just make a best guess, and the shrinkage prior should compress past a certain point when we don't need any more curves, all of them to just be flat lines. Now we can do something similar here for theta, but our feature vector is not functional, so we don't need this Gaussian process since it would be pretty weird if we were pretending our features were a function. What we want instead is we want this theta matrix to have a lot of zeros in it. And so what we're going to do is we're going to put the horseshoe prior that Evan described on elements of this matrix theta. And then again, we're going to apply shrinkage on successive columns with this same multiplicative gamma prior that Evan described. And we're going to share the shrinkage term for the columns of lambda and the columns of theta. So we're shrinking them both at the same time. Okay, and now we're through most of the building blocks that we need, and we're going to move into the demo portion. Could Debelina and Bora, could you guys stand up? So we're expecting there to be technical issues because we're coding. So if you guys have any problems and you want someone to come and help you troubleshoot while I'm talking, it's totally fine if you talk while I talk. I don't mind. And you should just raise your hand, and one of the people, Evan, Debelina, or Bora, will come by and try to help you out. Specifically, if you have a Mac versus a Windows, there can be some unique challenges to those. So I think Evan has a little bit more experience with Windows. So if you have a Windows and you have problems, maybe like flag him down specifically. But yes, and I wanted to pause also and see, since I know we're kind of talking for a really long time, if anyone had any questions now to address before we move into the demo. And that can hopefully also give you guys a chance to, if you have any issues right now that you want us to come look at, we can do that while you guys ask questions. If there's nothing, that's fine. I can keep going. Okay, so there are download instructions available online, and they're also in your handouts for today. And hopefully the most time-consuming bits of this installation are installing things like R and RStudio. So if you don't have that done already, I'm not positive that you'll be able to do it in time to catch up with what we're doing now. But you can certainly try. Oh. Uh-oh. Oh, I think it just came out for a second. Okay, we're good. Sorry. And so the package that we're working from is currently in development. It's all publicly available, but this is kind of a beta phase since it's not yet been published officially, and it's sort of for a paper that's in progress. So this will not be the static version that's around forever. We're currently working on it and updating it. And the demo code is also available on this GitHub repository. And once you've done the install of R and the package itself, the first step here is to load the package. And just to give you kind of a sense for what these demo slides look like, I'm including occasionally throughout these snippets from the code that's in the demo.r file. And so I'll kind of flip back and forth between the slide version of my code and looking at the code itself. And so I'm going to do that right now. This is what RStudio looks like for those of you that have it open. There's, I guess I'll show you the not filled with variables yet. This is what happens when you first open RStudio. The demo.r file here has a section that you should just run once. And then after that, it has the demo slides that I'm going to be going over. And for those of you that haven't used R or RStudio very much, there's a square here that for me is in the top left that shows the contents of the file that you're looking at. And then there's also a square that for your initial load will be blank that has plots that will show up throughout the demo. And then up here, there's an environment space that says what variables you have currently loaded. So for example, if I want to load the libraries that I'll need and the BES3FA package, I'll just highlight that section and I'll click Run. And now I have this dr.dat in my environment. So I'll flip back to the slides now. Oh, and one more thing I should note. Throughout, we have flagged which slide corresponds to which part of the demo. So here you can see that once we are done with slide 2, you should have run the slide 2 section of the demo.r file. And so now we're moving on to the slide 3 part. And so the bottom right here will show you the slide number associated with any given code section. So because we're doing a demo and the hope is that you can run this in real time if you'd like to, we're going to be working with simulated data. That has the advantage of being fast, like I said, so we can run it, but it also allows us to fix some true known parameter values so we can assess how closely our model estimates align with the truth. So here, this part of the code is just setting up values for our data simulation. The first line here is the random number generator. And for those of you that have a Mac and are running this, or a Linux, your results should look just like mine, because if we have the same random number generator, they'll align. For those of you that have a Windows, I think the random number works a little bit differently, so your results might look slightly different, but it should all still work and run. You just might not see the exact same simulated curves as I have. So here I'm going to go through what each of these settings are and just sort of describe what we're trying to do when we simulate data. The goal here is to come up with dose-response curves that look somewhat like actual dose-response curves, but we're going to use a reduced number of fake chemicals. So I'm setting the number of chemicals to be 13. I'm pretending that there are 20 unique doses that we observe response values at, and I'm pretending that there are 40 features in our feature vector. And then I'm also setting the dimensions of my shared latent space. So that would be the true number of columns in lambda and theta. And then I'm setting the dimension of the shared x specific space. So that's the additional variation in x that isn't shared with y. I'm also pretending that we have some noise in observing curves and also features. And then finally, with the real toxicology data, we don't actually observe the response at every possible unique dose value. We often just observe sort of snippets of dose response curves. So what I'm doing here is I'm setting the probability of any given value. Yes?
Can you say more about that? Are you saying that there's basically missing data points that you have a concentration range? Most compounds have data at every concentration, but for whatever reason, some don't.
Yeah. So what I've seen when I've looked at the ToxCast data, the raw format, is that there are some common doses at which most chemicals are measured, but we also have kind of a smattering of doses that we only observe a handful of chemicals at, and sometimes the dose response curves are shifted slightly. So what I'm trying to mimic here is that, say, we observe most dose response curves at these common, say, 7 dose values in ToxCast. That's the number of doses that you tend to see. But really, in ToxCast, there's 53, I want to say, unique dose values, and those sort of 7 common measurement points might not be the only ones that you see for a given chemical, and they might be slightly shifted, either left or right. And it may be that you observe, say, at dose 1, 2, and 3 for chemical A, but you observe at dose 3, 4, and 5 for chemical B. And so if you think of the world of possible dose response observations, the number of unique doses is 53, and there's, say, for ToxCast, for our example, about 2,000 chemicals. But since we don't actually observe all of those, we observe maybe 7 doses per chemical, then we have a ton of possible dose observations that we don't actually get.
Sorry, just to follow up on that. So each chemical, though, the dose 1 through 7, let's say they all had 7, this is a different concentration for that chemical. They don't correspond to the same concentrations?
So here, it might be easier actually if I just show a picture really fast. So if we look at, let's see. This is the adagene PXR assay that I was referencing earlier. And if we look at just an indicator for whether or not a chemical has an observation at a specific dose, this figure shows in red the points that we observe, and in yellow it's points that are missing. So each row is a chemical. So there's these common bands of observation doses. Does this kind of address?
Yes. So I think, and there's people in the room that can probably correct me that work for NCCT. John, I'm looking at you. But they when they were generating this data, it went through several different kind of phases, and I think there were slight adjustments to the protocol as they went. but then basically everything that was run within group was run the same concentrations, and then maybe not the same between different batches.
But there's different assays.
Use the mic, please.
Part of, sorry. So the different technologies, so your ToxCast is like 1,100 assay endpoints. Some of the cells tolerate different levels of the DMSO that's used to solubilize the chemicals. So depending on the assay technology that's used, they've had to use different concentrations. But then we got annoyed that we couldn't go as high as we wanted, so we made higher concentration solutions in DMSO and then repeated some of the assays. So yeah, I think the number of 53 is spot on in terms of the number of unique concentrations out there, but generally it's 7 or 8 point, half log dilutions down from some peak concentration, but we had trouble necessarily achieving the concentrations we wanted in every assay. So different assays should be mostly consistent.
But this is just the adagene PXR data only.
Okay,
right?
then that, if it's just adagene PXR, I don't know why the doses, well,
Because I think the top tested concentration in adagene was supposed to be 200 micromolar, right? But then some of the compounds couldn't achieve 200 micromolar, and so then they did half log dilutions down from whatever the top concentration was, and so that's why it could be shifted.
So I will say that for this specific simulated data set, it's more to show that we can knock out some big proportion of our data and we still can recover pretty well the loadings. So I'm not a toxicologist, so this is just the data that I was provided for the adagene PXR assay. It may be in a more cleaned form, so I will make sure to re-download the ToxCast database and see if this issue has been corrected. But if we assume that there is some proportion of our dose response curve or our possible universe of doses that is unobserved, we can mimic that by just setting a probability of any given observation being missing in our data set. And I'll show you kind of what that looks like in the next few slides. And then I'm using the adagene PXR assay data to simulate a basis for Y, so to simulate a loadings matrix lambda that's somewhat realistic. So that's all I'm doing here is setting real Y equal to this dose response data set that I'm feeding in. And so this function, the simulate data function, is just providing us with a simulated data set where we do know the true lambda, the true theta, the true dose response curves, and we have some simulated dose response observations.
Kelly, quickly before you move past that, could you comment briefly on your choice of K and J in terms of your dimensions of your latent?
Yeah, so in terms of the latent dimensions, I wanted to make K and J fairly small for time reasons, and also because most of the chemical dose response curves, I think in the adagene PXR assay, seem to follow sort of there's a few general shapes that they follow, so I wouldn't expect there to be like hundreds of functions contributing to these dose response curves, since generally it's either a fairly constant dose response, or we have this upturn or like a little bit of hormesis downturn at the end. So I think
Yeah, those are the only three models they when they're fitting the concentration response. That's when,
yeah. So there's the hill and the gain loss. Is that right? Or constant. So we're not ascribing one of those three shapes. We're allowing a basis to be learned. And here I'm just setting it to be 3, partly for I don't think there's too many crazy curves, so this should be a reasonable data simulation. And also just in terms of plotting, it's easier to see when you just look at a 3 by something vector than it is to see a 40 by something vector. Okay, so here's what the average dose response curves look like for our simulated data. The points show you the unique doses at which we could potentially observe data, and then the line is just connecting them for visual purposes. And there's a few example chemicals that I'm just pulling out. And here you can see what I meant by knocking out 70% of the data. The dots are what we actually observe in our data set. So for example, for chemical 1, we see a pretty strong dose-response relationship, but if we were to just look at the points that we observe and not the true line, we may not be able to capture the full shape of the data. So that's why we're combining information across dose-response curves and across chemicals. And like I said, these are simulated data. These are not real dose-response curves, but this is just to give you an idea for what our simulated data kind of look like. And then here's what the true factor loadings matrix lambda looks like. The k equals 3 is these 3 columns of the matrix. And then the colors here correspond to the value in that matrix entry. So 0 is the white here, and then a positive value is in green, and a negative value is in blue. And what you can see is that these are smooth. So we see kind of, I'm not sure, I think it's kind of hard to see the finer details on this with the projector, but there's smooth transitions between rows of this matrix, and the different rows of the matrix correspond to different doses. And so another way to visualize this is to look at the loadings themselves. So the first column of the loadings matrix is on the far left, and so we can see that, this dark green at the end is this end part up here where we get to a pretty high value in the loadings matrix. And so the first loading here could correspond to something like more toxic effect at higher doses. And if we look at this third loading, that could correspond to more of that hormesis downturn shape at the end. So that would be sort of an interpretation of what these loadings mean. And to see more explicitly how these loadings actually contribute to a dose-response curve Y, you can look at this relationship here, this yi equals lambda times eta I, as being a weighted combination of these loading vectors. So here the value of eta 1 is 0.59 for this chemical, so we're weighting loading 1 by eta 1, and then we're weighting loading 2 by eta 2, which is 0.71, loading 3 by eta 3, and then we add in the average curve, and that gets us to our true dose-response curve for chemical 1. And so these loadings vectors are shared across all chemicals, and all that changes is these weights, eta. And this is the weights is what we're trying to learn, because that's what tells us, you know, two chemicals with similar weights are similar in both structure and in response. Here's a quick visual of the entries of theta. The thing to note here is that we do have sparsity in our true theta matrix, so we have lots of white. And you can see that in another way here. We have a lot of concentration right at 0, and then we have some non-zero entries. And so our horseshoe prior should be able to recover this, we hope, well. So finally, we've talked a lot about prediction today, and our hope is that in addition to learning about lambda, theta, and eta, we also want to be able to predict dose-response curves for new chemicals. And so to mimic this, all I'm doing here in the code is pretending that for 20% of chemicals, we don't see any dose-response information. So I'm just creating myself a test set. Okay, so now we're getting to the part in the code where we're actually running the model. So to sort of recap, we've just been simulating data and observing what our true loadings matrices look like for our simulated data and looking at some of those dose-response curves. But now we're going to tell our sampler what the data are and what settings we want, and we'll let it loose. So if you recall, we don't, oh yeah, go ahead.
So we set that J and K.
Yes.
But we haven't really used them yet, right?
No.
Okay, all right.
Yeah, so good segue. We don't actually know K in real life, and we don't actually know J. So what I'm doing here is I'm kind of cheating, and I'm telling the model that I want K to be our true K plus some extra. And that's just to mimic a more conservative guess at what your true number of factors is. Because with the Bhattacharya and Dunson prior, what you can do is you can just give some conservative guess, and then the irrelevant or unimportant factors would be shrunk towards 0. And so in effect, you're you're going to capture the true number of factors, hopefully, and the rest will just kind of drop off. So here I'm setting, like I said, k and j to be some conservative estimate. Since we're Bayesians, we're running a sampler. I have a typo here. I say thin means to discard every 10th sample, but I meant to say keep every 10th sample. So we're just setting the model to run for 5,000 draws, and then we start saving, and we save 500 samples with every 10th sample kept. And then this post-process command here is telling the model that I want to run Evan's really cool rotational and sign ambiguity correction at the end of my sampler. So what that does is it makes all of the lambda matrices live in the same rotational space, and it fixes any label or sign switches. And then finally, I'm going to initialize my model parameters based on the singular value decomposition rather than just a random initialization. And it doesn't really matter what you set that to. I just thought I'd note which choice I made. And finally, you can run the sampler, and all it needs is, there's a lot of defaults for these settings. So if you're actually running it and you don't want to worry about, say, the burn-in or the post-processing or random initialization, you can just kind of leave all those things off, and the sampler will decide what to do. But I wanted to uncover here like what some of the more conscious choices you can make are. So for running the sampler, if you're still following along, this should take, I think, between maybe 30 seconds and a few minutes. And so while it does that, I wanted to go more in depth into what run sampler is actually doing. So what's happening under the hood here is that run sampler is taking a set of samples from the model posterior. And the problem here, as in a lot of Bayesian contexts, is that we can't directly use the model posterior because we can't write it down analytically. So what we do is we sample. And the way we do that is through a Gibbs sampler. And with our Gibbs sampler, what we're doing is we're kind of stepping around the parameter space, taking a sample of each parameter at a time, assuming we know all of the others. And it's really convenient because even though we don't know the model posterior, we do know the full conditionals of the model, which is to say that if we assume we know everything except for, say, the first row of theta, we can write down the distribution of the first row of theta. And if you're interested in Gibbs sampling and want to learn more, there's a link to some lecture slides on here, and I think when the slides are shared, you guys should have access to that. So back to what's going on in run sampler. There's some initial checks and such that happen that I just wanted to highlight. Since I'm not sure, probably this happens to not just me, but a lot of the times I try to run a model or some code that's out there and it crashes and I have no idea why. So I wanted to note, like, for example, when coming up with the package code, I wanted to make sure that, you know, if your number of chemicals that you're inputting for X doesn't match the number of chemicals that you're supposedly inputting for Y, it tells you, instead of just crashing the code and not giving you a warning. And then here's the parameter initialization. And this is where I input whether I wanted just random initialization or the SVD-based initialization. And then here are some hyperparameter values that we're defining. So this is sort of the stuff that lives in run sampler prior to actually doing the sampling. It's all the behind-the-scenes setup that happens to make sure that the sampler can actually run. And then if we look at the part of the sampler that actually samples, here we go through, as I mentioned, each of the parameters and hyperparameters, and we sample from the full conditional distribution. And so what it looks like here is, for example, we're sampling from theta, and then once we have our new theta sample, we sample from this beta squared theta term, which is one of the hyperparameters associated with theta, and then we move on to gamma squared. And so you can picture just sort of like moving in this circle, from parameter to parameter. And so we've looked from within run sampler at these other functions, but we can go even deeper and look within run sampler within sample theta at what's going on in there. And what's happening there is the sample of the full conditional distribution. And so if you're interested, you can write down the full conditional distribution in analytic form. And this is sort of the stuff that happens behind the scenes of this R package. Sorry if this was not interesting at all. I just thought it was good to kind of go a little bit in detail while we waited for things to run. So hopefully it's run for everyone now. And so here I'm showing on the left the truth, which we've already seen. This is the factor loadings matrix associated with the dose response curves. And on the right, we have the model estimated lambda matrix. And if you remember, we told our model that lambda should be 6 columns wide instead of 3. But what we can see is that it has given us really 3 columns and then 3 just 0 columns. So that's what we hoped for. But the issue here is that if you look, for example, at the first column of the truth and the second to last column of the estimate, they look very similar, but it seems like the signs have been switched. And similarly, if we look at the second column of the truth and the fourth column of the estimate, we have the same thing. If we look at the third column of the truth and the second column of the estimate, they seem to match perfectly. And that's because the lambda matrix is multiplied by eta. And so if, for example, we have the first column of lambda being positive and the first entry of eta being positive, that's the same as the first column of lambda being negative and the first entry of eta being negative. So even though we've resolved the rotational and sign switching ambiguity within samples with Evans post-processing, we haven't really compared our results to the truth because we don't know the truth in most cases. But since we know the truth here, we can run a quick post-processing thing to flip the signs and move our columns around so that our sampler looks like the truth. And so since we clean things up, we can now directly compare the first column of the truth to the first column of the estimate and see how closely they match. And it seems like it does a pretty good job, so that's good. The things to note here, again, are that we've shrunk a lot of the later columns to be pretty much 0. And also the sparsity in the original matrix seems to be well captured in our estimated matrix. We can also look at the lower and upper credible intervals. And what we see here is that we not only capture the matrix well, but it seems like we have a pretty low uncertainty and we aren't getting like wild upper or lower credible intervals to cause us concern. We can look again at the model performance of the true and estimated lambda, and we can also look at the lower and upper credible intervals for these. And since lambda looks so nice plotted because it's functional, we can look at a different view of the credible intervals for the factor loadings matrix lambda. Here, the red line is the true loading vector, and the middle dashed black line is our model estimate, and then the gray band is the 95% credible interval. So the thing to note here is that we have a fairly tight credible interval around the truth, and we seem to capture the truth well. Again, we're not just interested in how well we model lambda and theta. We also care about relating chemical distance and predicting for chemicals that we don't actually observe dose response for. So here, a lot of the time with distance, people will just perform PCA and then keep the first X principal components and then perform some distance measure on that. But here, since we actually have some representation of the important parts of our structure for toxicity, we have this eta factor here. We can just represent distance in eta space rather than representing it in X space. And that should give us a better estimate of distance that is only relevant to toxicity in feature space. And it won't account for the extra variation in features that aren't actually relevant to toxicity. So here's a quick view of how the model does in predicting or in estimating eta. The true eta is shown on the x-axis and predicted is shown on the y. So as we'd hope, we're kind of clustering about this x equals y line, which is to say we're doing a good job of predicting. And then similarly, the true distance is on the x-axis and the predicted distance is on the y. This would be the distance between pairs of chemicals A and B. And this is important because, as David introduced, we care about mixtures eventually. And I know none of this is mixtures right now, but hypothetically, if we can relate chemicals in terms of their toxicity relevant features, we can use, say, some distance metric to help us to estimate the main effects in a mixture model, and that'll give us more power to focus on those mixture components. So moving on to prediction. Here is a couple of the holdout dose-response curves. So these are two chemicals for which we didn't include the dose-response curves in the input deck. And we can see the red line here is the truth. The dashed black line is the model predicted true dose-response curve, and the gray band around it is the 95% credible interval. And again, we do pretty well, and we seem to capture the uncertainty also pretty well. So this has all been simulated data, and I want to highlight that that's not all that this model can do. The variables in X that I simulated were continuous, but we can also include count and binary data, which is important for toxicity relevant features. We're also allowed to have multiple observations per dose, which is important for the ToxCast data. And then unique dose levels need not be evenly spaced. Here I just evenly spaced them for convenience. And then, as I said, I included a small number of observations just for time components, but the real data set for at least a single assay that we've been interested in, the chemicals number in the thousands and the features number in the hundreds. So now I wanted to make sure there's no more questions before moving on. Yeah.
So someone online was asking about a graph like 5 slides ago where, where the plot with the green and blue, and they were asking what the green and the blue meant.
Oh, this one. Okay, so sorry, I didn't include the legend on these, but the blue is negative and green is positive and white is 0. So here, if you picture like these credible intervals here are represented by, lighter green and darker green. So that's a positive number that's a little bit lower and a positive number that's a little bit bigger. But here, since these last 3 columns are centered about 0, what we have instead is a mostly flat line that just has a small negative number for the lower credible interval and a small positive number for the upper credible interval. Is that? Okay.
And maybe I'll read, we had one more question online, and I'll kind of generalize it a little bit, asking about kind of what do you think about and how do you think through setting some of these parameters that you have to? Is there some theory or guidance, or is it really trial and error, or how are you doing that?
Yeah, so for example, let's see, let me go back. The hyperparameter values for the Bhattacharya and Dunson prior, there was a paper that came out, what year was that? A 2017 paper that specifically looked at the hyperparameter settings for that shrinkage prior and how different hyperparameter values impact your posterior. And for example, setting this number here, what I have as 2.1 now, and this one's 3.1. If you set them lower, I think there's less shrinkage. Is that right? There's some, Evan's more of an expert on this, but there's some weird high dimensional behavior that happens. And so for this specific hyperparameter, there's been research into what behavior you want and how to capture that behavior. So that would be an example of setting based on previous work and theoretical decisions. With other hyperparameters, often, for example, with the hyperparameter for observation noise, something that I've been thinking would be good to set would be to look at just the lowest dose of each chemical, and you could set a sort of more data-driven prior based on how much noise you have, just about like this, there's no activity dose for a chemical. But what we do is we just set a lot of sort of relatively uninformative priors, since, for example, we don't know very much initially about the specific entries of, say, the loadings matrix for a given,
So you have like one default set of hyperparameters that you would use broadly.
Yeah. So there's one default set, but then there are settings that you could twiddle if you wanted to modify. or like for the horseshoe prior, those hyperparameter values have specific shrinkage effects, and that's why we choose them. Is there any other questions so far? Yeah.
So I'm going to have to watch this a few times. but something I'm a little bit confused of that maybe should have been obvious is it seems like at the end of this that you're generating. Oh, I don't push the button.
No, just a little closer.
Oh, it seems like you're actually generating those response curves directly from the structural data for the chemical. And then you've mentioned a few times about doing similarity based on this reduced dimension space, right?
Yes.
So how similarity isn't being used to generate those responses. What are you saying? You would use similarity for a different purpose, or
yeah? So we're not explicitly using similarity here, but
okay.
My point was mainly that when we were initially thinking about this issue, it sort of came about because we read a paper that was looking at predicting dose response curves, kind of like this. And what they did was they used principal components and picked the top, 40 PCs and used that as a measure of similarity just based on those principal components. And we sort of wondered, well, is there a better way to do that? Because the feature space isn't necessarily, at least in the mold 2 case where we're not specifically selecting features that we know are relevant to toxicity, it's not, the sources of variation in that space are not necessarily related to the toxicity. And so you could then use something like this as an input to later models, which I think will become more relevant when we get more into our mixtures of exposures.
Okay, I have more questions, but I'll wait.
So my thought now was that I was going to show some quick results, preliminary results with the Adagene PXR assay, but my thought was that for a lot of the parts of the code in demo.r, we've flagged things like try me, where you can mess with settings. So if anyone is more interested in messing with the code than hearing me talk, you can just ignore my talk about the real data results and start messing with the code and rerunning things. I will say that if you change a thing and rerun it, I would just start from slide 2 and rerun everything, because I'm not sure if it will break things if you just like change this line and then move on from there. So just rerunning everything is safer. But if you have problems while you're doing that, feel free to raise your hand and someone will come help you out. Having said that, I'll go through a really quick glimpse at the real data results. So here we put in as entries the true. Oh yeah. So, oh boy. So it's very desaturated on this screen. There's one pretty dominant loading vector, and that's pretty much all you can see on your guys' screen. But on my screen, I see more subtle other columns, so I'm sorry. But as I was saying here, what we put in as inputs for Y was the Adagene PXR assay, and what we put in as inputs for X was the mold 2 structural features. And so the loadings matrix lambda, just a quick look at the first 4 columns. Column 1 is this sort of traditional dose response thing that we see over and over again. Column 2 is something similar, but with a slightly different shape. Column 3 is a more negative dose response relationship, and column 4 is sort of a dip and then a rise. So we are seeming to capture some basis for the space that at least seems to be fairly intuitive in terms of dose response. And then if we look at theta, which I think, yeah, it kind of looks also very washed out. But again, the thing to note here is that here our rows are our different mold 2 features. And I know I've been saying 777, and here there's only 600 and something. That's because for the specific chemicals in this data set, there were a lot of features that were not unique. So for example, if you have a feature that counts the number of some weird radioactive isotope or something, and all of the chemicals don't have it, then that is basically just an empty feature vector that you don't need. So we could throw out a lot of those feature vectors. And so we really only ended up with like 620 that we used in the model. But the thing here to note is that we do have a lot of sparsity that our model has captured. And you can look and you can say, okay, we have this first column that seems pretty dominant in our lambda matrix, and that's associated with this first column of our theta matrix. And here's a close-up look at the first 30 features of our theta matrix, just to get more of a visual than this gives you, because the 600-dimensional matrix is hard to see. And what we can do is we can say, okay, so for this matrix, we have a lot of zeros, but for the non-zero entries, what do we have that's related to this first sort of classic toxic curve? And what we see is things like average of molecular weight, average valence vertex connectivity, order 0 index. And if anyone knows what these are, can they please tell me? But what we have is a way to take a learned basis vector and take these features and relate them. And we can say, like, here is the shape, and here is the features that are related to the shape. And we haven't done this yet, but what we want to do now is talk to chemists and toxicologists and see if this makes sense. And as David was saying, we want to get better feature vectors so that we can sort of maybe try to tease out this relationship that we're uncovering. And so here's a quick visual. I mentioned getting a distance metric from the predicted values of eta. And so if I look at I think I picked out the first 5 closest chemical pairs in eta, and I picked a couple that were active and a couple that were not active. So here's a pair of chemicals that's considered very close together in eta space. And you can see that they have very similar dose-response curves on the left. These are the observed dose-response values. And then on the right, I show the structural features here. And these are 17 beta estradiol and 17 alpha estradiol. So they are very similar. And our model is saying that they're similar. So that is a good sanity check. And then here's a pair of chemicals that appear to not be very active. And once again, they're very similar in both structure and dose response. And our model is saying that they're similar also in this latent eta space. The chemicals that are far apart in eta space are typically something really weird, like this ketone thing. And this just has tons and tons of chlorine, so it lives kind of in its own world relative to other chemicals, I think. But what we see is here that our model is saying that, you know, ketone and mercuric chloride are very different in this latent eta space. And if we look back at the dose response space and the structure space, they appear very different in those spaces as well. So another sanity check. Similarly, we can see the same thing with sodium iodide and murex. And if we look at predictions, so this is with a 20% holdout set. So I took 20% of our chemicals that were in the data set and I held out their dose response curves, but I included their structural features. And I asked the model to predict what our observation estimate and 95% credible interval was for those curves. And here I'm showing you some predictions for chemicals that seem to be fairly active. And on the left, I have a couple that don't have very many replicates per dose value. And on the right, I have a few examples that do have a high number of replicates per dose. And the thing to note here is that if you look at the shapes of these active curves, we seem to be sort of generally capturing this traditional dose-response curve shape, and we appear to be fitting the data fairly well. And if we look specifically here at benzolide, we're not getting that Hermesis shape, and it seems like we are getting a narrower confidence interval, which is good because these chemical dose response observations for benzolide appear to have less variance than some of the other chemicals that we're looking at. So I feel like generally we're seeing not only decent estimates, but also capturing the uncertainty relatively well in terms of coverage, but not being super conservative and having crazy credible intervals that way overcompensate. And then if we look at inactive chemicals, these are chemicals that have a relatively flat dose-response relationship. we see sort of a similar story where we're capturing the data relatively well. And so that's sort of a snapshot of the data results. These are not complete by any means, and I still need to sort of pit this model against competitors, and that's a work in progress. The paper should be available at this archive link hopefully by the end of the summer. And the rest of the team and I have been also working on exploring sort of other chemical structure data sources outside of MOL2. We also want to not just look at one assay at a time. We want to handle multiple assays. Possibly some of the transfer learning ideas that were talked about earlier would be relevant. And then we also want to not only look at just straight up structure and ToxCast output, we want to look at how this relates to human health outcomes, because that's sort of the end goal of all of this. And then, as David mentioned, we're also very interested in nonlinear dimension reduction techniques and how they could be incorporated in this framework. I think that's all I've got, but I'd be happy to answer more questions. And if people want to play around with the simulation or talk to us, we can hang out.
It was really, really nice work and fun for me, at least. From memory, the Adagene PXR assay is one of the most, if not the most, promiscuous assay in the ToxCast library.
Yes.
So it probably has the highest number of active chemicals. So I'm assuming that's why you started with it.
Yes.
So how does this do against assays that have very specific biological targets and therefore have incredibly sparse data matrices?
That's a really good question, and that's something that I want to look at. With simulation would be a really good way to do that. You could just pretend that tons of your chemicals are constant. But I haven't done that yet. It's a thing that I've thought about. I think maybe a way to model that more explicitly would be to maybe do a mixture of, say, this model for active chemicals, and then you could just say there's also some probability that they're just constant. And so you would only learn the shape for active chemicals, and for constant chemicals, you would just assume white noise. But yeah, that's a very good point.
And then my next question is with, so I have a lot of ideas for different chemical structural sources you should try, so we can talk about that offline. But also, have you thought about looking at physicochemical properties? Because the OPERA model that I was talking about earlier, we have predicted physicochemical properties for pretty much the entire DSS Tox database, which encompasses all of the ToxCast and Tox21 chemicals. So that might be another way to enrich this.
Yeah, that would be great to include. Thank you.
So I don't know what all your features were, but they looked like they were continuous features. What have you had binary vector input with this kind of approach work?
So with the MOL2, we do have binary. I can't remember specifically what some of the examples are, but the way that the code handles it is to assume that it's kind of like probit regression. We assume that there's some latent continuous truth, and then our binary indicator is just whether or not that truth is above or below 0. And so that can fit really neatly into the factor model framework, because we just care about that latent underlying continuous variable rather than caring about the 1 or 0.
So MOL2 is actually like mixing these binary features with these continuous features?
Yeah,
and
MOL2.
You're handling the binary in this special way, and you don't think that they're being somehow the value of information in that feature is being affected by this treatment?
That's a good question. I haven't thought deeply about whether some features have more valuable information, but I would say that generally my thought would be that if a feature is kind of garbage and doesn't tell us anything, it would just get zeroed out in most of those theta columns or theta rows. And so that would be a good thing to test, would be to sort of insert simulated garbage features and see how the simulation handles it.
Okay, thanks.
Thank you.
Thanks again.